Hey physics fans, I'm Captain Phillips and I'm here to talk to you about course problem 14.1. So go ahead and take a moment, pause the video and read the problem statement. So what here sticks out to you and points you towards what kind of physics we're going to need to use to solve this problem? Well, I've been told about different masses, a tension force, but most importantly, I'm also told that this system is in static equilibrium. And that's going to let us know that the net external forces are equal to 0 and the net external torques are equal to 0. So what am I being asked to solve for? Well, my task here is to solve for the maximum allowable mass of that hanging mass such that we don't break that horizontal wire. What physics am I going to need to use? Well, Newton's second law for rotation, as well as the definition of torque and the magnitude of a cross product. We've already been given a picture of this problem, so let's take that, put it in here. And my givens, I've been given the mass of the beam, as well as this maximum allowable tension in the horizontal wire, and the angle theta that the beam makes with the horizontal. Now let's point out that this theta is not the same theta referred to in my magnitude of a cross product. There, it is the sine of the angle between those two vectors when placed tail to tail. The theta I've been given is simply the angle between the beam and the horizontal. So we'll need to use that later on in this problem. Finally, for our assumptions, I'm going to assume that this is a uniform beam, and that allows us to say that the weight force, which acts at the center of mass of the body, is also at the center of the body. Now it's time to solve this problem. So the first thing I do is I draw my free body diagram as normal, isolating the bodies. I place my forces on here. I assign a coordinate axis, and I break up any of my forces that don't align with that coordinate axis. And from there, I list any critical dimensions that I might have. Now for solving this problem, I start with the equation that's on the PRC as listed. So Newton's second law for rotation. Here I'm now going to list the torques caused by each of those forces on my free body diagram and set that equal to 0 since we're in static equilibrium. Now, I'll have you note that because I'm going to choose an axis of rotation about that pivot point A, this means that when I sum the torques about that pivot point, the vertical and horizontal components of the normal force are not going to provide any torque in our system since they act at the axis of rotation I've chosen. Thus, their displacement from that axis of rotation to the application of the force is 0. As I continue on, I see that the torque caused by the weight force of the beam, R1, which is the magnitude of that displacement, times the weight force itself, times the sine of the angle between them when placed tail to tail. Now note, this angle when placed the displacement vector and the force vector tail to tail, that's actually 90 minus the angle theta that we've been given in this problem. Using geometry and trig, I know that the sine of 90 minus theta is the same thing as saying the cosine of theta, which is what I'm going to write here. Continuing on, I have the torque caused by that hanging mass, which is R2 times the weight of that hanging mass times, again, the cosine of theta. And finally, the torque caused by that tension in the horizontal wire, which is R2 times the tension times the sine of theta. Now notice the sign of this term is negative. That's because when I conduct that cross product, R2 crossed with T, I see that that direction is opposite the coordinate axis that I chose, and so I'm going to list it as negative. Finally, I'll note that R1 is equal to the length of this beam divided by 2, and that comes from our uniform beam assumption. And R2 is going to just be the length of the beam. Substituting these values in, and solving for that mass 1, I get this expression for the maximum allowable mass of mass 1. Now we're going to check this. So I see sig figs. Well, this is an algebraic solution, so this doesn't apply. Units, I can do dimensional analysis here. So in this first term, I have the maximum tension, which would be in newtons, divided by the acceleration due to gravity, which is in meters per second squared. And so that term is going to be in units of kilograms, which I would expect. And our second term is also in units of kilograms. Thus, my mass would be in units of kilograms, which checks out. Is this reasonable? Absolutely yes. And that wraps it up for us today, physics fans. Well done. I'll see you next time.
Hello. Goodbye.